Welcome to XT Pro, the data processing software for duct runner pipeline mapping systems. To launch the program, double-click on the XT icon. Enter your password in the opening screen. Then, press OK. In the screen that follows, you can either start a new project, or open an existing project. Let's first explore starting a new project. If you opted for the single-entry software upgrade, you will be prompted to select the type of measurement you performed. The options are, double entry, where an entry and exit point coordinate are available. Single entry, where an entry point coordinate as well as a waypoint coordinate for guidance are available. Single entry, where an entry point coordinate as well as a highly accurate start heading are available. We will first explore the recommended standard procedure, where both start and ending point coordinates are available. This option is also the default option if you have not upgraded to the single entry software. The first step is to enter project log information. Log data is linked to the raw data file that was generated by the probe, which is important because it helps to identify the source of the data when revisited at a later date. The project identification can be any unique name or number associated with the pipe segment. For the purpose of this tutorial we will use Brussels. The project date refers to the day that the pipe was mapped. As default, the current date is displayed, but this can be changed manually if necessary. Next, select the core business of the customer. For this tutorial we will select water. Then select whether the reference coordinates are metric or imperial standard. It is likely you will work for the same client more than once. So rather than entering the client details each time, you can add the client information to your list. For the purpose of the tutorial, the client name is Brussels Water. And the address is Grand Place, number 1, in Brussels. You can delete clients from the list at any time by clicking on Delete from List. As you will have learned in the chapter on operational procedures, the recommended procedure for mapping a pipe is to pass the probe through it 4 times, twice from A to B, and twice from B to A. After 2 runs, the probe is turned around and reinserted into the pipe, backwards. The recommended probe orientation for the 4 runs then is forward, backward, backward, forward. If you have followed the recommended procedure, the input in the probe orientation sequence field will then be F, B, B, F. Although identifying the field operator is optional, it is recommended to complete this field in case any questions are raised about the project at a later date, and input from the field operator is required. The project description field is optional. You can enter any aspect about the project you wish to remember, but doesn't necessarily flow from the data. Next, enter the latitude of the pipe's location. Latitude is a critical input. It is used to eliminate the impact of the Earth's rotation as the probe travels through the pipe. In the drop-down menu, you find the locations already stored. Brussels is not yet listed, so needs to be added. To add the location, enter Brussels in the new location field, and enter the latitude in degrees and minutes. Click on Add to update the locations list. An easy way to obtain a latitude is to Google latitude and the location name. Now it's time to enter the pipe's specifications. First, enter the pipe's internal diameter, in our case 90 mm. Then, enter the pipe's external diameter, in our case 110 mm. Proceed to select the pipe's material, in this case HDPE. And select the pipe's medium, in this case, potable water. Although optional, it is useful to identify the pipe's owner, or end user. In our case, the owner and client are the same entity. But the owner often differs from the client, for example when your client is the contractor installing the pipe. Pipe owners can be added and deleted as described earlier. Last but not least, you can indicate whether the mapped pipe is part of a bundle, or not. In most cases, you will be tasked to map just one pipe of a bundle. Along the way, however, the rest of the pipes in the bundle can be located above, below, to the left, or to the right of the pipe you mapped. If you indicate that the mapped pipe is part of a bundle, we recommend that you enter the details of the bundle size in the project description field. For example, bundle size is 4 × 110 mm HDPE. This additional information enables users to reduce the risk of third-party damage to the pipe bundle. You have completed this page, click Next to proceed. Now we must enter the coordinates of the start and end points of the pipe. There are many coordinate systems in the world, and often there are multiple systems within a country. Therefore, it is important to enter the name of the coordinate system in which the start and end points of the pipes are mapped. If your coordinate system is not yet in the list, you can add it in the usual way. Our data requires Lambert 72, the national coordinate system of Belgium. You can add a name to the start and end point coordinates. In this example we use south and north, but you can also use a manhole number, if applicable. Or, in the case of horizontal directional drilling, rig side and pipe side. Now, enter the X, Y, and Z coordinates of the system entry point A. Do the same for system entry point B. Typically, these coordinates are determined by a chartered surveyor on the day of mapping. But if that is not possible, they can be surveyed on another day, as long as the end points of the pipe do not move. In our case, the given coordinates refer to the top of the pipe. However, it is also possible to enter center of pipe coordinates, or invert of pipe coordinates, whichever is easiest to obtain. Please note that the coordinates must both be taken at the same level. Regardless of the level of the input coordinates, the output can be saved at top, center, or invert level. The default frequency of output points is 1 point per meter. However, the system logs data 100 times per second, so at a traveling speed of 1 meter per second, the sampling frequency can be as high as 1 point per centimeter. Of course, a lower frequency is also possible. The last input required is the configuration of the system that passed through the pipe. Extraction is configured to operate with one probe only. The details of the probe for which it is configured are listed in the gray fields and cannot be changed by the user. What can, and must be defined, is the wheel set configuration used for the measurement. Depending on the type of probe, the wheel unit type, and their wheel ID, can either be found on the odometer wheel, or in the quick reference guide supplied with the set. Simply select the right code from the drop-down menus. At this time you are ready to download the data logged by the probe to the computer. We will first show you a short video on the process of correctly connecting the probe to the computer. Now that the probe is connected and turned on, start the transfer of data by clicking on the Download Data button. The bit counter indicates that downloading is in progress. Do not interrupt this process. However, should the connection be broken for some reason, simply restart the download. No data will be erased until you manually instruct to clear the probe's memory. After the download is completed, first, save the dataset. Dataset 1 refers to the first log session for a particular pipe segment. A dataset usually contains multiple runs. In this case, dataset 1 contains 4 runs. The graph displays the raw data from several sensors. The red-blue lines display the counters of the 2 odometer wheels. These lines clearly show the expected 4 runs in this dataset. The green and blue lines are the raw output of 2 accelerometers, and clearly show the difference between movement and stationary status. Clearly, 4 runs are distinguishable, confirming that all data was transferred successfully. The probe's memory can now be cleared. Click on Clear Memory, and then on OK to confirm. After about 5 seconds, a message appears that the clearing process has completed. The probe is now ready for the next measurement. Before processing the data, we do recommend to switch the probe off to save battery power. Proceed to the next step by clicking on Go to Process. The main screen of the processing phase displays the same raw data of 2 accelerometers as the previous screen. As a reminder, the 4 runs in this dataset are pointed out. Each run must be processed separately. To isolate the data of the first run, slide the left marker approximately to the middle of the start calibration period. Then, slide the right marker approximately to the middle of the end calibration period. The software will only process the data between the 2 markers. Click on Process Selected Run. You will now be prompted to confirm the run number in the dataset, which is 1. Because this run followed the recommended operational sequence, the software knows the probe traveled from A to B in the forward direction. When processing is completed, you are prompted to save the data. The software creates a unique file name using some log information. We recommend you do not change the name. Click on Next Run to proceed. Isolate the data of the second run by sliding the markers to the middle of the start and end calibration periods. After clicking on Process Selected Run, you will again be prompted to confirm the run number, which now is 2. The software already knows the probe traveled from B to A in the backward direction. Again, the software created a unique file name. D1 stands for dataset 1, R2 stands for run 2, BA is the direction of travel, and B indicates that the probe moved in backward direction. Proceed to process the third run. Make sure you avoid placing the markers in small areas of noise in the calibration period. Between runs 2 and 3, The probe was turned around, so run 3 travels from A to B, in the backward direction. And finally, process run 4. When you place the markers, you can fine-tune the placement by clicking on the arrows on the side. Alternatively, you can enter a specific sample number to which the marker should jump. After each run, you can review key diagnostics. The odometer calculation results are presented in 2 ways, as calculated pipe length traveled, and velocity. The graph portraying the pipe length traveled, shows both odometer lines move in unison, indicating no slippage of wheels. You can zoom in on any section of interest. The blue line is the best fit used by the software. The velocity chart shows that the probe traveled at about 1 meter per second. The erratic pattern indicates the probe passing a heavy weld. RPA stands for roll, pitch, and azimuth. Roll refers to the probe rolling around its own length axis. Pitch, or inclination, refers to change in the vertical angle. And azimuth refers to changes in the angle to true north. The roll graph of run 4 shows that the probe started the run at a roll angle of about 20 degrees, and during the run smoothly rolled to -180 degrees, or a total roll of about 200 degrees. The pitch graph shows the typical pattern of an HDD profile, whereby the probe starts the run with a negative pitch angle, then gradually leveling to about a 0-degree angle as the HDD profile bottoms out. And finally a positive pitch angle as the pipe curves up towards the exit point. When viewed in the depth profile graph, the typical HDD shape is confirmed. The azimuth graph shows 2 significant areas of directional change in the horizontal plane. When viewed in the top view graph, the shape shows a relative short bend, followed by a short straight, and then a longer bend, again, confirming the azimuth graph. This completes the tutorial for extraction. We highly recommend that you also watch our tutorial on using XView software, and the tutorial on troubleshooting procedures. Meanwhile, enjoy our products, and if you have any questions, please contact your local distributor, or send an email to info@reduct.net.